example of Kirchhoff's laws, and I think it's quite a good one to show that the numbers can sometimes be quite confusing, but as long as you follow the rules, you're fine. Okay. Now, what I've done in this question, I've kind of modified it. When the original version of the question doesn't have any arrows on it. In other words, it doesn't tell you what direction of a loop to take, and it also doesn't tell you the directions of I1, I2, and I3. And as you'll see, this is getting a little bit confusing. So what I've done is I've just decided to put I1, I2, and I3 going in some direction, and we'll see what happens. So you'll notice here I've identified a junction, and I've decided for myself that I1 and I3 are going into that junction, and I2 is coming out. Okay. Well, if we're applying Kirchhoff's first law, well, what that says is everything in equals everything out, and so therefore I1 plus I3 is equal to I2. Notice here the naming convention may be a bit odd here. Okay, in that you normally have 1 plus 2 equal to 3, but in this case, that's the way that it goes. That's the way that the problem's been set up. So I'm just going with that. It doesn't really matter what the numbers are here. I'm then going to take the two loops that I've identified. Now, in this case, I'm just going to go clockwise. The reason I'm going clockwise is because I know that those EMFs will stay positive as long as I go clockwise. If I go anti-clockwise around those loops, those EMFs are going to become negative. Okay, so we're going to apply Kirchhoff's second law. Now, at this point, it's probably worthwhile thinking about our two potential differences in here. That's the two resistors. Well, the current going through resistor at the top there is 20 ohms at the top. It's got current I1, because if you notice here, it's in series with this loop here. Okay, and so therefore, the potential difference there is just I times R is 20 times I1. Similarly, in our resistor down at the bottom there, we've got 20 times I3 because we're connected in series with our circuit I3 there. And the top loop here, the red one, is really the tricky one because if you notice, as I said before, our EMF is positive here because we're going around the loop. Okay. However, we notice that as we are going through this resistor here, we're going in the opposite direction to the current. The current, if it's going down on this wing or this leg of the journey, is going to be going left. I am going right, and so therefore my potential difference is going to be negative there. Okay, what that means then is if I take the sum of the EMFs around this loop, there's only one, that's 10, is equal to the sum of the potential differences, again, there's only one. I'm going to have 10 is equal to minus 20 I1. In other words, I1 is equal to minus 0.5. Okay, so we've got a minus number there. Now, you might be a bit sort of confused as to what a minus sign means in this case. We'll come to that in a second. We'll then take the blue loop. And the blue loop is slightly nicer because, again, we've got a positive EMF because we're coming out of positive and into negative. Okay, we come round, and this time we're going in the same direction as I3, so we don't need to worry about any minus signs there. We've got 5, which is our total EMF, is equal to 20 times I3, okay, and then we're just going to do a bit of division. We then want to get I2. Well, I2, we're going to go back up to our Kirchhoff's first law. We know I3, we know I1, and so therefore we can just add those together and we get minus 0.25. So we're left with two negative numbers here. Now that's not very satisfactory, okay, however, this is just the way that we've pointed this out, that we've started this out. Now, this is where it gets perhaps confusing, but also it can be kind of looked at in a slightly different way. We've decided that, for example, that I1 is going down into that junction. If I've got a minus sign, that means that there is negative current going into that junction. Well, in other words, what that means is that there's going to be positive current coming out of the junction. So actually, what I've just done there is I've kind of got my direction wrong. Similar for I2. Actually, something should be going in rather than out of the junction in that branch there. And this is what I mean about setting up the problem in a certain way. As long as you've set it up correctly, then you're fine. Now, to illustrate this, what I've done is I've built the circuit here. Okay, I've just put the ammeter, I think I put it in a slightly different place. Let me just check there. 1, 2, 3. Okay, no, ammeter's in the same place. Okay, and you'll notice there that the values are the same. 0.5, 0.25, and 0.25. The only difference here is our minus sign. Okay, and the difference there is to do with, as I've just said, the direction. Okay, is to do with our direction. Now it gets even more confusing because here we're looking at the direction of the electrons. Okay, if the electrons are moving down, then what that means is my current is moving up. Remember, conventional current flows in the opposite direction. So I'm just going to click on this value, and then you'll see a slightly more satisfying result there, right? Whereas I have said that current in this one here was going in, actually it's coming out. And again, where my I2 value was coming out of the junction, it actually should be going in. I3 is fine, and that's why my I3 value is a positive one and not a negative one. Okay, so I guess the point here is this could get very confusing. Okay, the way you set up a problem, the way that you think about how those values could be confusing. But as long as you stick to the rules, as long as you decide on a particular setup and maintain the rules of Kirchhoff's law, you will get numbers that actually make sense. And I'll reiterate, those minus numbers simply mean that the current is actually going in the opposite direction. Now, the danger of that is it gets up a conversation about whether current is a vector, whether it has direction or not, but we'll leave that for another time. For now, just be happy that Kirchhoff's law, although it is confusing, actually makes a lot of sense if we take the time to think about the numbers. Thank you for watching.